Convergent plate boundaries are plate boundaries where plates are moving together. I'm going to show you 3 examples of different configurations, and it all depends on what crust is involved. Okay, let me move my face out of the way. So in this first example, this convergent plate boundary is 2 plates that are the leading edge here is continental crust. So the Indian Australian plate is continental crust, as is the Eurasian plate. And what happens when those 2 plates come together is the mountains pop up. So we get fold and thrust mountains. These lines in here are big thrust faults, and they grow the Himalayan mountains, and they pop up the Tibetan Plateau. So there's no consuming of plate here. It's just the growth of these really high mountains during continent-continent collision. Another example would be when old, dense oceanic crust subducts underneath younger oceanic crust. So in this configuration, oceanic crust is on both sides. So the example here is the Japanese island arc. We could also use the Aleutian island arc as well. This is a subduction zone. In the middle, marking the subduction is the trench, very deep basin or trench in the ocean. And on the other side of the trench is going to be a chain of volcanoes. So in this example, Japan is a chain of volcanoes where the Pacific plate goes down, it melts, and that melted material comes up to form the islands of Japan, which are volcanoes. The next example, we have on the left here oceanic crust, and on the right continental crust. So the first example of a convergent plate boundary 2 slides ago was continent-continent collision. This example is continent-ocean collision, and the other one in between was ocean-ocean. So in oceanic crust, continental crust collision, the oceanic crust is going to always be the one that subducts. It's dense basalt material, and it subducts beneath the more buoyant, less dense continental crust. The example here is this Nazca plate subducting underneath the South American plate, giving us the Andes Mountains. Right, turn my face back on. Hello. So the plates are coming together. They're different configurations, ocean-ocean convergence. One plate descends beneath the other. We call that subduction. Marking the point of subduction is the trench. It's a linear feature. Water is going to go down with that subducting slab, the old oceanic crust, and that water is going to mix with the hot mantle. It promotes melting. So there's not just melted mantle material everywhere. There's got to be something that promotes the melting. In this case, it's the wet sediments. They act as what's called a flux. So flux melting. Trying to get the glare off my glasses. There we go. I'll just look sideways. Okay. Next is ocean-continent conversion. So continental crust doesn't subduct. The oceanic crust does. And when it subducts, it's going to go down into the trench, and it's going to melt, bringing that water down, and that's going to come up as volcanoes. So examples here are the Andes or the Cascadian volcanoes. The last kind of plate boundary is a transform plate boundary. And in this case, the plates are sliding side by side. The biggest example we have in the world is the San Andreas Fault. To the north of the San Andreas Fault is that Juan de Fuca plate, which is subducting to give us Cascadian volcanoes. To the south is that area of Baja California, where you get down far enough and you have a spreading center. So in between those 2 different things happening is the San Andreas Fault, and it is a strike-slip fault. The plates are moving side by side past each other. So there's no volcanoes, but there are large earthquakes. Here's an image of it. The kind of faulting is called a transform fault or a strike-slip fault. And those are fractures where there's just displacement. There are earthquakes, but there's not going to be any volcanoes. One of the last bits of evidence for plate tectonics was the discovery of magnetic stripes. They took a boat with a magnetometer trailing off the end of it and picked up magnetic signals. What they realized was the signals are stripes, and the stripes are symmetrical across the mid-ocean ridges. So they found anomalous highs and lows. Those magnetic stripes, they don't make a perfect stripes, but they found that they were stripes symmetrical across the ridges. Comes to find out, what's happening is the basalt crystals within the iron crystals within the basalt are crystallizing oriented with the Earth's magnetic field, and sometimes the Earth's magnetic field flips. When the Earth's magnetic field flips, then the iron crystals, when they form, are going to be forming in a different direction. So they have names, these reversals do. The Gilbert reversal epoch, the Gauss, the Matayuma, the Bruges. And so that led them to believe that like these Gauss rocks were at the ridge at the same time. They formed and moved away from the ridge. Okay. So another piece of evidence was looking at the ages of the rocks on the seafloor. So these are color codes, and the red rocks are the youngest and the blue rocks are the oldest. So just looking over here at the Atlantic, red in the middle, those are rocks that are forming today, and to the sides, this blue, those are the very old rocks that used to be, that formed, 180 million years ago at the mid-ocean ridge, and they have since moved away from the mid-ocean ridge. To review, let's look at this again. So plate tectonics, we have those convection cells that are setting up the motion in the asthenosphere as hot material rises and cool material sinks. There's also this idea of driving plate tectonics, that the topographic high at the mid-ocean ridge actually pushes on the oceanic crust. And then on the other end are the subduction zones that are slabs of heavy oceanic crust that are being pulled down into the subduction zone. Okay, ridge, push, slab, pull. And then at the plate boundaries, we have convergent, divergent, and transform. Plates moving apart, plates moving together, and then transform motion as they're sliding side by side.